Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, count stepping numbers in the range. The problem is very interesting. It is a very straightforward application of digit DP. We have already discussed this technique in this channel. If you have watched that video and understood it, I would strongly encourage you to pause right away and try to solve this particular problem by yourself. If you haven't watched that video, I would encourage you to watch this video completely and then revisit the other video and solve the problem discussed there by yourself so that you can get a more thorough understanding of this topic. I would link the previous video somewhere in the description down below or in the top right eye section. You can check it out. So with that, let's get started. The problem states that you are given two positive integers low and high represented as strings. You have to count the number of stepping numbers in the range low to high. What is the stepping number? Stepping number is an integer such that all of its adjacent digits have an absolute difference of exactly 1, right? You have to return this integer modulus 10 to the power 9 plus 7 because the answer could be very huge. So let's take an example. Let's say low is 1 and high is 11. You have to return the number of stepping numbers in the range 1 to 11. So there are these are the stepping numbers which are possible. Everything between 1 and 10. 11 is not a stepping number. Why? Because you can see there is one digit which there are two digits which are adjacent, but they don't differ by exactly 1. So they don't satisfy this criteria, and because of that 11 is not a stepping number. So there are 10 stepping numbers between 1 and 11, and hence the answer here is 10. Now let's take one more example, 90 and 101. Basically you have to find the number of stepping numbers between 90 and 101. So only two stepping numbers are possible, 98 and 101. You can see here the difference between every adjacent digits is exactly 1. Again here difference between any two adjacent digits are exactly 1. No other numbers between 90 and 101 is a stepping number. For example, 90 itself is not a stepping number because you can see there exist two digits which are adjacent but they don't differ by exactly 1. So because there are only two stepping numbers, the answer here is 2. So hope the problem statement is clear. Now notice one thing, the value of low and high can be up to 10 to the power 100, and because any 64-bit integer can't store this long value, they have given this low and high as strings to us, right? And because of this only the value can be very huge, and we have to return it model 10 to the power 9 plus 7. Now given this constraint, it should be very clear right away that you can't do brute force. By brute force I mean you can't iterate over everything between low and high and see whether each numbers are stepping or not, and by iterating over each of the digits. So you can't do that because iterating over between everything between low and high would take 10 to the power 100 iterations, which will surely not pass the given time constraints. So we need to do something smart. So let's see how to solve this. So we need to find out the number of stepping numbers between low and high. As always, if possible, try to reduce the number of variables that you have in the problem statement. In this problem we have like two variables low and high, and in any problem like this which asks you to find anything between a range L to R, one of the things that you should think is can I break it into two parts? Basically I will say, okay, I will find out everything between 1 and H, and I will find everything between 1 and, let's say, L minus 1, and then I will subtract these two to get everything between L and H, right? So can we do this here? The answer is yes, because here what we need to just find the count. So if we count the numbers between 1 and H, and if we count the numbers between 1 and L minus 1, we can subtract these two, and that will give us the number of valid stepping numbers between L and H. Now notice you can't do this, you can't apply this optimization in other problems, or first of all, like why this is an optimization, because you can see now you need to solve only one problem with one variable. So either there will be h or there will be l minus 1. So there is only one variable. So what you can say, okay, I will write a function that will give me the number of stepping numbers between 1 and x, and I will just do f of h minus f of l minus 1, and that will be my answer. Now you can't apply this operation every time. For example, let's say if you have been asked that, okay, find the bitwise OR of everything between 1 and h, or find the bitwise OR of everything between l and h, you can't apply this exact same trick. Why? Because if you find the bitwise OR of everything between 1 and h, and you find the bitwise OR of everything between 1 and l minus 1, there is no opposite operator of bitwise OR. So you can't apply any operation that will remove exactly these all elements. Because of this, you can't apply this exact same trick, and in that case you have to deal with these two variables. You can't skip one of them. So hope this point makes sense. So now the for like follow-up problem here is, we have to just find out the number of stepping numbers between 1 and x, right? Now, as we know the definition of stepping number, we have to, every number should satisfy these two criteria. The number should be less than equals to x, and the difference between any two consecutive digits should be equals to 1, right? Now let's say this is x 62541, and we need to find how many ways are there to fill these 5 boxes. So for simplicity, let's remove this criteria as well. So we just need to find out the number of numbers which are less than x. Some of you might be thinking, okay, what the shit it is. Basically, we already know the number of numbers which are less than equals to x. It is simply 62,541. But notice the numbers are very huge. You can't store it directly in an integer. That's why you are given those numbers as a string, and you have to return it modulo 10 to the power 9 plus 7. So even this problem is not that trivial. You can use some mathematics to solve this problem, basically counting the number of numbers which are less than equals to x modulus sum m. You can do this very easily, not very easily, but you can do this using mathematics in order and time, where n is the length of the string. But let's say you don't need to, we need to do something else. We don't want to go into that mathematics solution. Then we just need to find out how many ways are there to fill these 5 boxes, such that whatever numbers we will get, all those numbers should be less than equals to x, right? Now, what are the possible ways to fill the first box? We can fill, in usual scenario, there are 10 digits, 0 to 9. You can fill it anything between 0 to 9, but you want it to be less than equals to x. So because of this, you can only fill this first place with anything between 0 and 6. You can't put 7, 8 or 9 here, because if you put 7, let's say, or 8 or 9, the number which will be formed will always be greater than x, no matter what you will put here. Even if you put all zeros here, this number would be greater than x. Why? Because this is this 7 says that this number is actually greater than equals to 70,000, and your number is just 62,000 something, 60,000 something. So you can't use 7 here. Just to make this point a bit more clear, let's say you need to compare two strings. You need to understand which of these two strings are greater. So what you will do, you can simply iterate over the strings one by one, or iterate over the digits one by one. Find the first non-matching digits. The first non-matching digits will give you the idea which number is smaller. Whichever is smaller in the first non-matching digit, that number will be smaller. Note that this number is smaller even though these digits are much greater than the original digits, but because the first digit where they are not matching is smaller in the first number, this number would ultimately be smaller, right? So hope this point makes sense. And in case if you're thinking about what about the numbers which are not of same length, let's say 6220. In that case, you can simply pad it with 0 to make it the same length and apply the exact same algorithm to figure out which number is smaller, right? So with this point, we now know that we can only fill the first digit with anything between 0 and 6, right? Now let's say you put 4 here, just an example. So if you put 4 here, what are the ways you can put, or how many ways are there in which you can fill this particular digit? You can fill this with anything between 0 and 9 now. Why? Or rather, you can fill any of these digits with any digit of your choice. Why? Because you put a 4 here. So when you are comparing these two numbers, you already find a non-matching digit, right? And if you remember, we just have to find the first non-matching digit, and this will be the first non-matching digit. And because this number, in the first non-matching digit, this number has the smaller value, no matter what you put here, this number will always be smaller than the original number x, right? So if you put anything which is less than 6 in the first place, you are free to put in any digit afterwards, right? Now let's say you put 6 here. In that case, you don't have a non-matching digit, right? So because you don't have a non-matching digit, you are not free to choose anything. Basically, when you will be comparing these two numbers, you will be skipping over and you will be looking at this digit as well. And because this digit will be looked at, and this digit can be the first non-matching digit, you are bound to put everything which is less than equals to 2. If you put anything which is greater than 2, this digit would be the first non-matching digit, and in this non-matching digit, the second number would be greater. So this number will always be greater than x. So that's where, if there is no non-matching digit beforehand, you are bound to put everything between 0 and this index, right? So let's again say that you put 2 here, just for simplicity. Now in that case, again you will go like this number can be the next, can be the first non-matching digit, and in that case you are again bound to put everything between 0 and 5. So hope this point makes sense. Basically, if you are trying to fill the ith digit, what matters is whether there is already a non-matching digit before I or not. If there is already a non-matching digit before I, you are free to choose anything at I, that is, you can put anything between 0 and 9. If there is no non-matching digit, then you can only put everything between 0 and this particular digit, right? So hope this point makes sense. So basically, we just need to make sure that, or we just need to have the knowledge that what is the small, like whether there is a non-matching digit before the current index or not. So let's say there is let's start from the scratch. Let's say we are maintaining this is smaller as well, which denotes whether the number is already smaller or not. In other words, this denotes whether there is a non-matching digit or not in the prefix, right? So initially, when you are filling the 0th position, is smaller will be false. Why? Because there is no non-matching digit before 0th position, right? So because is smaller is false, you are bound to put everything between 0 and 6. You can't put anything greater than 6. So now, based on what you will put here, is smaller will be either true or false for the next index, and based on that you will put, or you will select the next index. So in other words, you want, like, how many numbers are there, or how many ways are there to fill these 5 boxes if is smaller is false. And then what you're saying is, based on, let's say you put 4 here, then is smaller would be true because there is a non-matching, is a non-matching digit, right? So in that case you will say, okay, how many ways are there to fill these 4 boxes such that is smaller is true. So isn't this problem exactly similar to the original problem? Original problem was how many ways are there to fill these 5 boxes if is smaller is false, or basically is smaller is anything between true and false. Now how many ways are there to fill these 4 boxes if is smaller is true or false? So hope you can see the recursion here. So basically, if you have a function that takes in two things, this is smaller and the index, and this gives you how many ways are there to fill all the boxes starting from I based on whether you have a smaller digit before or not. So if you have this function, then what you can simply do, you can simply do this kind of logic wherein you will start with is smaller false, because that will be false for the 0th index. Now for 0th index you have say this 7 choices, either you will put 0, 1, 2, 3, 4, 5 or 6. Now based on what you put, is smaller value will change. So if you put 0 here, then these two digit will differ, and if they differ, you already have a non-matching digit. So you will say, okay, I have a non-matching digit, so is smaller would be true, and I have to fill everything after 1, right? Now similarly, if you fill 1 here, you will say count me the number of ways such that is smaller is true, and I have to fill every box after 1. In the same fashion, if you put 2, count me the number of ways to fill everything after the first box if is smaller is true. Now finally for 6, if you put 6 here, then this is non-matching, like this is matching, right? So in that case you don't have non-matching digit at all. So again you will say count me the number of ways in which I can fill these 4 boxes such that non-matching is false. Basically there is no non-matching digits, right? So once you get the value of all of these, you can just sum them all up, and that will be the result, or basically that will denote how many ways are there to fill these 5 boxes, right? So let's look at one small example to make this a bit more concrete. Let's say you have to solve for 21. You have to count the number of numbers which are less than equals to 21. So you will start with false 0. Basically you are saying that, okay, I have to fill 2 boxes starting from 0. I have to fill 2 boxes, and I am starting from 0. So first I will fill the 0th box, and then I will fill the first box. So because this is the first box, there is no digit before it, so there is no non-matching digit as well. So you will start with false. So now you have 3 choices. Either you will put 0, or you will put 1, or you will put 2. So if you put 0, this is the state. Basically you will say I put 0 here, so there is non-matching digit already. Because there is no non-matching digit, you make it true, and you will say, okay, I will count how many ways are there to fill this box if non-matching is true. Similarly, if you put 1, this will be true, 1, and if you put 2, it will be false, 1. Now if it is true and you have to fill this first box, it means you already have a non-matching digit. So you are free to choose anything here. So you can put anything between 0 and 9 here. So you will put 0, 1, 2 all the way up to 9. If you whatever you put, because you already have a non-matching digit, all of them will have non-matching digit, right? So basically you are saying that I have filled this box. Now I have to fill, let's say there is another box, and I have to fill this. For this box as well, there will be a non-matching digit, because this was the non-matching digit, and if there is a non-matching digit for the first index, the same can be true for the second index as well. So basically we have done everything as true here, right? Now this is also f of true of 1, so basically it will expand very similar to this. And f of false of 1, basically we are saying that there is no non-matching digit before 1, so this can be the first non-matching digit. So we want to make sure that this is smaller, so we have only 2 choices, either 0 or 1. So we can fill it with 0 or fill it with 1. If you fill it with 0, it will be true, 2. If you fill it with 1, it will similarly be false, 2. Now can you count the number of numbers? So from here you will get 1, because you crossed everything, like you have filled everything. So basically if you filled everything, you found one way to fill, right? So you get 1 from here, you get 1 from here, you get 1 from here, like from everything between 2 and 9, and you will get 1 from here as well. So in total you are getting 10 here, right? So value of f of true of 1 is 10. So you are getting 10 from here. In the same fashion, you will be getting 10 from here as well, because they are exactly same state, f of true o comma 1. From this, will be getting 1, and you will be getting 1 from here. So in total, you will be getting 2 from here, right? So in total, you are getting 10 plus 10 plus 2, which is 22. So we are saying that there are 22 numbers which are less than equals to 21, which is true. Basically, you will include 0 as well. Like this entire thing will include 0 as well, because there is a way in which we fill both the box with 0. So it includes 0 as well, and you can see if you include 0, there are exactly 22 numbers which are smaller than equals to 21, right? So hope this entire solution makes sense. What will be the pseudocode? The pseudocode would be very straightforward. We will have two things with us: is smaller and index, and based on whether is smaller is true or false, we can either go all the way up to 9, or we can restrict ourselves to the value at digit of index. And based on that, we will start from 0 to all the way up to ed, and we'll calculate what is the new is smaller as well. Basically, if is smaller is already true, it means if there is already a non-matching digit before. So if there is already a non-matching digit, that digit will continue to exist. If there is no non-matching digit, then it depends whether the current index is ed or not. If it is ed, then if it is not equals to ed, then there is a non-matching digit. Basically, the current index can be a non-matching digit. If it is ed, then in that case everything is matching. So you will have to pass false here again. So we will just do this for everything between 0 and ed and sum them all up to get the answer, right? So hope this entire solution makes sense. What is the time complexity? Time complexity is simply number of states multiplied by what we are doing inside each state. So what is the number of states? Each smaller can take two values, either true or false. Index can take n values, where n is the length of the string. So there are total 2 into n states. And inside each state, what we are doing, we are iterating over all the digits. So there are total d digits, let's say. So this is the complexity, n into d. Now this this is the solution for a reduced problem. If you remember, we have to solve this problem where the difference between consecutive digits is also equals to 1. But we have removed this constraint for the simplicity reasons. Now let's bring back this constraint. Let's say we need to find out how many numbers are there which are less than equals to x, and the difference between consecutive digits should also be equals to 1. So let's say you filled the first digit with 4. Now if you fill the first digit with 4, what are the choices for the second one? Again, is smaller will be true because there is a non-matching digit. And second, for this one, you will have all the choices between 0 and 9. You can put anything between 0 and 9. Now which one, like, can you, if there is a restriction that consecutive digit difference should always be equals to 1, can you put this anything between 0 and 9? Answer is no. Basically, now you have to understand what you have put in the previous digit, and based on that you will put something here. So in this particular criteria, you can only put either 3 or 5. So basically everything between 0 and 9 are applicable, but only 3 and 5 between 0 and 9 has absolute difference of 4, absolute difference of 1 with 4. So basically now you have only two choices here, 3 and 5. So based on what you will fill, let's say you fill 5 here. So in that case, again for this one you will have all the choices between 0 and 9 because there is already a non-matching digit. So in that case, you are free to choose anything between 0 and 9, and you also want that the difference between adjacent digits should be exactly 1. So basically, although you are allowed to put anything between 0 and 9, only two allowed values for second constraints are 4 and 6. So you are bound to put either 4 or 6 here, and based on what you will put here, the next one will follow. So basically, apart from knowing So previously, to fill a particular index I, you just need to know whether there is a non-matching digit or not. But now to fill a particular index I, you need to know whether there is a non-matching digit or not. That is true, because you need to understand what all are possible here. But apart from that, you also need to know what is the last digit you have filled. Otherwise, you can't satisfy the current second conditions, right? So in your state, you will also add one more variable which will say what is the last digit that you have filled, and based on that, you can skip some of uh, you can skip filling some of the values here if the second condition is not satisfied, right? So I would strongly encourage you to pause and try to at least write the pseudocode for this particular solution by yourself. So this is how the pseudocode will change. So notice that we only introduced last, and as we have discussed previously, based on whether the difference is 1 or not, we will be either picking I or skipping I. Notice that I is still between 0 and ed. Again, this will be not equals to, sorry for that. But I is still between 0 and ed. But we have to abide by the second constraint as well, and for that we have said that okay, we are filling the current position with I. So we'll just check whether the last index that we have filled, whether the difference between last and I is 1 or not. If it is not 1, you can't fill I, right? As simple as that. So once this condition is satisfied, you will do the exact same things, and notice that because you have filled the current position with I, now for the next index or for the next box, the last element is I, so you will put I here, right? So now what is the time complexity? Time complexity is again the number of states multiplied by what we are doing in each state. What we are doing in each state doesn't differ, it is still D, or the number of digits that we have, but number of states differ. Like there are two different values of E smaller, true or false. There are D different values of last, because there are D possible digits, and there are N different values of index. So the complexity now is N into D square, right? So this will pass the given time constraint because D is up to 10, like there are only 10 possible digits, and N is up to 100, like the size of the length of the string is 100. So this will surely pass the given time constraint, or very easily pass the given time constraint. Now there is just one small trick or one small edge case that you need to tackle. So previously, if you remember, previously we were starting with false comma 0, right? But now we have a last as well, like we have one more element last. So now where will you start from? You can say okay, I will start from false comma something comma 0. So what you will put here? You can say okay, I will put 0 here, that last index is 0, but that will not give you the correct result. Why? Because if you put last index as 0, you are indirectly saying that only 1 is allowed here, nothing else is allowed here, right? But because this is the first index, you are free to choose anything between 0 and 6, right? Even if you put 2 here, that will not uh, that will not denying the condition second constraint as well. So basically second constraint is the difference between two adjacent digits should be exactly 1. So even if you put 2 here, the second constraint will still be satisfied because there is no previous digit at all, right? So because of this, if you put 0 here, this will not give you correct result. So one possible approach could be you will say okay, I will start everything between 0 and 9. So basically I will first call f of false comma 0 comma 0, and then I will call f of false comma 1 comma 0 comma 2 comma 0 comma 3 comma 0, and so on and so forth, and that will give you the correct result. That is fine. But there is something else you can do. Let's say you don't need to iterate over the entire loop. Again, iterating over the entire loop is completely fine, and that will give you more optimal solution. But in case you don't want to iterate over the entire loop, what you can say, notice what was the issue you were having. The issue was you don't need to use this condition at all if what you are filling is the first position, right? So what you can say, okay, if index is not 0, then only you will do this constraint. So basically this if, you can modify this if by saying that if index not 0 and absolute of last minus I is not equals to 1, then you will continue, right? So in that case you are free to choose anything here, but there's a catch. The catch is, even though you are free to choose anything here, this index 0 might not be the first index always, right? Why? Because let's say you have two digit number 12, so 12 will be represented by 00012, right? So this you will not like, you don't have to apply the constraint on this digit because this is the first starting digit, right? So this digit you don't have to apply the constraint on, but with this logic you will still be applying the constraint on this digit because this is not the, because as per you this is not the first digit, but this can be the first digit depending on if you have put all zeros before, right? So you might have already guessed, we need to somehow maintain what is the starting digit, or whether the current digit is the starting digit or not. So just one more thing, you can simply add one more thing here, if it is the start position or not. So if it is the start position, then you will not apply this condition, right? So the algorithm would slightly modify to something like this. Basically, instead of maintaining if it is a start position, I've maintained that whether the string has already started or not. So if the string or if the number has already started, in other words, if there is a non-zero digit that we have taken into account already, then I will apply this constraint always, right? So in other words, what we are saying is, if the number has already started, then I will apply this constraint. If the number is not started, it means we are still searching for the first digit, then I will not apply this constraint. And that is exactly what we want. Now, with this, one small change would be, you have to maintain, or you have to keep updating is started as well. And what is the logic? Logic is whether you have found any non-zero digit or not. So if you have already found a non-zero digit, then it's fine. The number is already started. If you haven't found a non-zero digit, and if the current I is non-zero, then only is started will be true. Otherwise, it will be false, right? So hope this point also makes sense. Now we will start with f of false comma false comma 0 comma 0. Now notice that this thing doesn't really matter. You can start with f of false comma 1 comma 0 as well, and it will give you the same result. That is, there's no issue with that. So with that, I hope you understand the entire solution. If you have doubts in any of the piece that I discussed, feel free to post that in the comment section below. I would be happy to answer. Again, one more thing, if you have understood the solution, I would encourage you to pause right away and try to code this by yourself and try to get it submitted as well, because that's where you will be able to grasp this concept for a longer period of time. And as mentioned in the starting of the video, there is already some problem that you have solved using this technique in the past. I would link them somewhere in the description down below. You can check it out. So next we're looking at the code. Again, I am assuming that you have already at least tried this coding yourself. Otherwise, I think there is not much use to be true. So the solution is straightforward. We have this DP array for maintaining the state. Basically, we have these four things in the state. If you remember, is smaller, is started, index, and what is the last element, right? That we have taken. So we have maintained this 4D array to store the state, so that we don't need to recompute the same state again and again. Now, what we are doing, as we have discussed, the function is straightforward. We just simply count the number of valid numbers, or in other words, number of stepping numbers between 1 and high, right? And then we are finding out the number of stepping numbers between 1 and low minus 1, and we are subtracting that, and that will be a result, right? Now subtract one function is simply subtracting one from the given string. We'll look at that. But this count valid is simply finding out the number of numbers which are smaller than equals to s, which are stepping. So inside this we are doing the exact same thing. We are finding out ed, which is based on is smaller. Basically there is already non-matching digit or not, and inside this we are iterating over everything between st and ed. And as discussed, this is the condition to skip a current number. Basically we need to check if it is already started. If it is started, we have to make sure that the difference between adjacent digits is not 1, and then we will update the is started and is smaller based on their respective criteria and add it to the result and continue. Now finally, this subtract one function is very straightforward. We need to subtract one from a string. Let's say you have to subtract one from this string. So what you will do, you will find the first non-zero character from the back and just subtract one from there. So let's say you have to subtract one from 200. In that case, you will find the first non-zero character, you will subtract one from there, and you will make everything else to 9, right? So that's what we are doing. We just reverse this entire thing. So this will become 022, 002, and then we find out the first digit which is not 0, and we subtract 1 from there. So we find out the first digit which is not 0, we subtract 1 from there, we fill everything else up till that to 9. So we fill this to 9. So this will become 991. And finally, we reverse everything to return the result. Now this is one small edge case that you need to handle. Let's say the number was 100. So in that case, if you subtract 1 from here, it will become 099, right? So you don't want to return 099. Instead, you want to just return 99, right? So that's where we are then iterating from the front, and we are popping out all the 0 numbers, right? So that's what we are doing here, and finally we reverse it and return it. So hope this entire thing makes sense. Again, if you have any doubts, feel free to post them in the comments below, and I hope you learned something new, and I will see you in the next one. Thank you.